So far we have discussed about the state feedback control design problem for a generic case where we have assigned the eigenvalues to some desired location. The further classification of that generic state feedback control design problem are two. First is the regulation problem, and second is the tracking problem, which we will discuss later. So the regulation problem deals with the fact that suppose the reference signal R is 0 and the response of the system is caused by some non-zero initial conditions. The problem is to find a state feedback gain so that the response will die out at a desired rate. Now this computation of the desired rate is basically consists of defining the objectives, the control objective, which you can define in terms of the eigenvalues, that where you want your eigenvalues of the closed loop system to be placed. So there are many examples. So the first one, the aircraft cruise control or the liquid level control in tanks. Uh, so if the So consider the plant described by the pair ABC. If the system A is already stable, then it is pretty much clear that for the zero reference signal and for non-zero initial conditions, the response of the plant would be stable. It would tend towards zero. But in that case, you won't be able to achieve certain desired rate. So we need to design a state feedback controller K so that we could place the eigenvalues to some desired location. Now if A is unstable, then for any non-zero initial condition, the response will grow unbounded. Now to first of all, we need to make the closed loop stable, which we have done so far by using this control signal as R minus K times X, where K is the feedback controller which we need to design, such that the response caused by the non-zero initial condition is given by this. So we have seen this equation a number of times, and this is only the response due to the initial conditions, but the response due to the external signal reference R would be 0 because the reference signal is 0. So this problem could be pretty much dealt in a similar way what we have done so far about designing the state feedback controller design. The more involved problem is the tracking problem, where suppose the reference signal R is a constant or R of t is some or let's say the magnitude is A for t greater than equal to 0. The problem is to design an overall system, that is the closed loop system, so that the response phi of t approaches this reference signal at A as t approaches infinity. So this is called the asymptotic tracking of a step reference input. Now within these two classification of the state feedback control design problem, now if you put R of t as or A is equal to 0, then the tracking problem would reduces to the regulator problem, meaning to say that for the first implication of this one, that for any given A, if we design the controller as a regulator, then would it be possible that the tracking would always happen for any non-zero constant reference signal? So the answer for this would be certainly not, because it would depend on the DC gain of the closed loop system also. So the first question rises, then why do we then study these two problems separately? So the straightforward answer to this one, that most of the linear systems what we are discussing are derived basically by linearization of a non-linear system around some operating point. Now these operating points may change from time to time depending on the operating conditions. So whenever the operating condition changes, the reference signals would also change. So we need to ensure that for the same system, when we do the linearization around different operating points resulting into different reference signals, that all those signals should be trackable. Now there is, so suppose now if the reference signal is no longer a constant signal, or it is a time varying signal, let's say a sinusoidal signal, then that problem is called a servo mechanism problem, and that problem is a much more difficult problem. So we won't be addressing the servo mechanism problem, but along the solution of the tracking problem, those problems could also be dealt with. So now we will see that how you can achieve the tracking for any constant reference signal. So to address the tracking problem, in addition to the state feedback, we also need a feed forward gain P defined by this. So now if you see a structure of the state feedback system, this is the state space system where we have two outputs, let's say Y, and so suppose we also have the measurement of the state, and this is U. So far we have considered the design of the state feedback controller by considering K, taking the feedback from X and putting it back to the state space system. Let's say this is 0, or say for example, let's put it R of t. So this would be plus and minus. So here U would become R of t minus K times X. But here we have also introduced another degree of freedom by P, which would turn into another gain P by a reference signal R. Okay, so now we have two degrees of freedom for the designing of the controller. One is the state feedback gain K and another is this P. So this is the control structure. So this complete part we will call the controller, and this is nothing but this equation ut is equal to PR minus Kx. Now here we need to design two gains, one is P and K, such that the Y becomes equal to the reference signal or to a constant value A. Consider once again the transfer functions what we had seen earlier for the pair ABC denoted by G hat S. So this transfer function is written for n is equal to 4. Okay. So we have seen earlier all these beta i's and alpha i's of the plant. Now after applying this state feedback and the feed forward, the overall transfer function of the closed loop system would become from Y hat over R hat. Okay. So the transfer function, so the denominator would contains all the eigenvalues, all the desired eigenvalues denoted by or written in terms of a characteristic polynomial and their coefficients with this alpha I bars, and the numerator won't change as we had seen earlier. Now in addition to this overall transfer function, we have additional parameter P associated to the overall transfer function. So if AB is controllable, if the original AB pair is controllable, then all the eigenvalues of the state feedback of the new state feedback state matrix A, including the state feedback gain, or equivalently all poles of this GF hat can be assigned arbitrarily. This is one of the results we had studied earlier. Now under this assumption, if the reference input is a step function with magnitude A, then the output Y of t will approach the constant G hat f at 0 dot A as t tends to infinity. So we are interested in computing what would happen to the Y in time domain as t tends to infinity, which is equivalent to computing the DC gain of this transfer function also. And the DC gain can be computed by putting s is equal to 0 in this overall transfer function. So if I put s is equal to 0, all this part would go away, and similarly all this part would go away, and we would have Y hat of 0 is equal to G hat f 0 times A, because A is the DC value of the reference signal. Now as all these numerator and the denominator part will go to 0, the remaining part is beta 4 by alpha 4 bar, and we want this G hat f of 0 is equal to 1, in that case only we would have y hat is equal to r hat in the steady state. So on the right hand side we would have p times the ratio of beta 4 by alpha 4 bar. So if we substitute p as the inverse of this factor, which requires that beta 4 should not be equal to 0, the tracking would be possible if and only if the Planck transfer function g hat s has no 0 at s is equal to 0. Right? Because if there is an s, if there is a 0 available at the origin, then we know that the numerator cannot be changed. The roots of the numerator polynomial cannot be changed. So this s would stay as it is. If this s stays as it is, then the DC value would definitely be 0. Now in that case we cannot track any reference signal because the response would always be 0, since the denominator is always a stable Hurwitz polynomial. Right? So if we compute p by this, then so there are two design parameters, the state feedback gain k, where first we have computed so that we could place the eigenvalues at the desired location. The second design parameter has been computed such that the tracking to a constant signal is possible, which is computed in this way. Okay, so this is one of the important results.